Hey there, and welcome. Today we're going to try to see the invisible. We are diving deep into the secret world of gases. The stuff that's literally all around us, but we almost never stop to think about. So let's start with something really simple. Think about a party balloon. It's full of air, right? Or helium if you want it to float. But what's actually happening in there? What's the secret life of the stuff sealed inside that rubber? Well, that's what we're here to find out. All right, so to begin, we're going to put on our old school scientist hats. We're going to look at gases the way people first started to understand them, by focusing on the things we can actually see and measure, the big picture properties. First on the list is pressure. This is that constant push the gas exerts outwards. Just imagine a tire. The air inside is constantly pressing against the inner walls, keeping the whole thing firm. That push, that force, that's pressure. Next up, you've got volume. And this one is pretty straightforward. For a gas, volume is just the size of its container. But here's the cool part about gases. They'll always expand to fill up whatever space you give them. A tiny box, a huge room, doesn't matter. And number 3 is temperature. We all get this one, right? Hot or cold, Celsius or Fahrenheit. But for this explainer, what scientists use is an absolute scale called Kelvin. And trust me, the reason why they use it, well, that's a huge clue to the biggest secret we're going to uncover. Okay, so this is where things start to click. Early scientists realized that these 3 things, pressure, volume, and temperature, they weren't just doing their own thing. Nope. They're all connected by these really simple, super predictable rules. So, for example, you have Boyle's law. It basically says that if temperature stays the same, pressure and volume have this inverse relationship. The harder you squeeze a gas, increasing the pressure, the smaller its volume gets. It's just like squeezing a balloon in your hands. So simple. Then you've got Gay-Lussac's law. This one links temperature and pressure. If you heat a gas up inside a container that can't expand, its pressure shoots up. This is exactly why your car's tire pressure is higher on a really hot summer day. The heat makes the air inside push way harder. So having all these individual rules was great, but it felt incomplete. It was like they had different pieces of a puzzle, and it strongly suggested that there had to be one single unifying equation, like a master key, that could put it all together. They just needed one more piece. And that missing piece was something called the mole. And no, not the little furry creature that digs up your lawn. In science, a mole is just a word for a specific number. It's a way to count things. Kind of like how a dozen always means 12. Well, a mole means a specific and frankly unbelievably huge number of particles. It's how we count the amount of gas. And how huge are we talking? This huge. That's Avogadro's number, 602 sectillion. That's how many atoms or molecules are in just one mole. It's a number that's so ridiculously big, our brains can't really even process it. But it was the key. So with that last piece of the puzzle, the mole, which we call N in the equation, they finally found it. The master key, the ideal gas law, PV equals nRT. This beautiful little thing connects everything: pressure, volume, the amount of gas, and temperature. All those other laws we just talked about, they're all wrapped up right inside this one elegant formula. Okay, so this is incredible, right? We have an equation that lets us predict exactly how a gas is going to behave. But that just opens up a much deeper question. Why? Why does it work so perfectly? What is actually going on with all those trillions of invisible particles inside the balloon that makes them obey this mathematical rule? To answer that, we've got to do something amazing. We have to zoom in, way in. We need to shrink ourselves down and leave the world of things we can see and measure and enter the secret, invisible world of the molecules themselves. So this is what it looks like down there. It's total chaos. You have just a massive number of tiny particles zipping around at insane speeds in completely random directions. They're so far apart from each other, it's mostly empty space. And they're constantly smacking into each other and bouncing off the walls of the container like a 3-dimensional game of pool with billions of balls. And believe it or not, this chaotic picture of constant motion, that's the key to the whole thing. It is the physical reality that explains all of those laws we saw earlier. It turns out Everything we measure on the outside is just the giant collective effect of all this tiny motion on the inside. Now, to get this, we just need one quick concept: kinetic energy. It's a super simple idea. If something is moving, it has kinetic energy. That's it. The faster it moves, the more kinetic energy it's got. And here is the big reveal, the secret. Temperature is just what we call the average kinetic energy of the gas particles. When we say something is hot, all we're really saying is that its particles are moving, on average, really, really fast. And cold, it just means they're moving slowly. That's the whole secret. Heat is just motion. So what about pressure then? That steady push we feel? Well, it's not steady at all. It's the grand total of trillions upon trillions of those little particles smacking into the walls of the container over and over and over again every single second. It's a constant, furious bombardment that from our perspective feels like one continuous force. Now, it's important to note that this beautiful picture, this ideal gas model, it works amazingly well for most situations. But it is not a perfect model. And the real world, as you know, is always a little bit messier. See, the ideal model pretends that the gas particles are just points, that they have no size at all, and that they don't attract each other even a little bit. But in a real gas, the particles do take up a tiny bit of space, and they do have these super weak little forces pulling them together. For the real sticklers for accuracy, there are more advanced equations, like the famous van der Waals equation, that actually account for these little details. So, we've gone from a simple party balloon all the way down to a hidden universe of constant, chaotic motion. We've discovered that the big things we feel, like temperature and pressure, are really just the shadows cast by this invisible world of movement. Which leaves us with one last really big question to chew on. If heat really is motion, what happens when you cool something down so much that all that motion completely stops? What's left at absolute zero?